Hello everyone, I'm Yanxun and I will explain theorem 1.9.5 and 1.9.6. Theorem 1.9.6 says that if a function has a closed interval as its domain, and the function is continuous on the interval, then the function is bounded. And theorem 1.9.6 further states that the function can attain its minimum and maximum values. Theorem 1.9.6 gives us some conditions. 1. The function has a closed interval as its domain. And 2. The function is continuous on its interval. Both can determine that the function is bounded, and these two conditions are necessary. For example, the function f(x) equals 1 over x. X is defined on this interval. We use a proof by contradiction. Assume that the function is bounded, and its absolute value upper bound is m. M is greater than or equals to 1. Then we can choose x prime equals 1 over m plus 1 and plug it into the function, which is greater than m. Its conjugate to m is upper bound. Therefore, the function is unbounded. This example shows that if the function is continuous, but the interval is not, then the function is not necessarily bounded. Another example is that if the function is discontinuous, but its domain is a closed interval, then the function is not necessarily bounded. For example, we define g of x when the absolute value of x is less than or equal to 1. The function g of x equals absolute value of 1 over x, and g of 0 is defined as 0. And the domain of this function is the closed interval negative 1 to 1. But the function g of x is discontinuous at 0. X equals 0. Let xn equals 1 over n. When n goes to infinity, xn goes to 0, but g of xn equals n goes to infinity, not equals to g of 0. Therefore, g is discontinuous as x equals 0, and g of xn goes to infinity, which shows that the function is unbounded. Back to the proof. We want to prove theorem 1.9.5, which says that if a function has a closed interval as its domain and the function is continuous on the interval, then the function is bounded. Okay, then we can give any function f that is continuous on the closed interval a to b, and its range is on the real numbers, and assume that it is unbounded. Because the function is unbounded, we can assume that for any positive integer n, there exists xn in the interval a to b, and the absolute value of f of xn is greater than n. But according to the Bolzano-Weierstrass theorem, there exists a subsequence xnk that is convergent. Since f is continuous and its limit xnk x0 is in the interval a to b. But according to theorem 1.7.6, a convergent sequence must be bounded, which contradicts to absolute value of f of xnk greater than nk. Therefore, the function is bounded. Then we will use theorem 1.9.5 to prove theorem 1.9.6. Briefly speaking, because the function is bounded, it has a greatest lower bound and least upper bound. And because the domain is a closed interval, we can find an extra number in the domain that makes the function f equal to the least upper bound and the greatest lower bound. It's the end of my presentation. Thank you for listening.